Today we are going to be talking about capacitors. So a capacitor is just another form of temporary energy storage that's used in circuits. So we're going to go through this much like we did with inductors the other day. We're going to talk about what they physically are and then get into how they behave. So the most common form of capacitor is what's known as the parallel plate capacitor. And as the name suggests, a parallel plate capacitor consists of two parallel conducting plates. So here is our top plate. And then below our top plate will be, you guessed it, our bottom plate. Like so. Okay. So this is a circuit element that we can see literally contains an open circuit. And we're going to see that it works that way in DC circuits here in just a little bit. There is not a means of electrical conduction that is separating these two plates. In fact, in the overwhelming majority of instances, a dielectric material is placed between these two plates, which I'm going to draw as this pink box here. And the purpose of this dielectric material is to enhance the electric field that is sustained between the capacitor plates. So this dielectric material plays an analogous role to the core material in our inductor, right? So when we make an inductor with a core that has a very ferromagnetic material, it can really enhance the amount of magnetic flux that's stored inside of the inductor, thereby increasing the amount of energy stored by the inductor. For a capacitor, if we put a high dielectric material in between the plates, it is enhancing the amount of electric field that can be contained within that region, thereby increasing the amount of energy storage. Okay. I'm going to throw some dimensions at you guys really quickly. For this particular device, we have some particular length, L, some particular width, W, so that the product of L times W is the area of the plate. And then there is a gap separating the plates, labeled as D. And so geometrically, the capacitance of a parallel plate capacitor is given by epsilon A over D, where that epsilon is related to the dielectric medium that's between the plates. So the larger that epsilon value is, the larger the capacitance is, and the more effective the device is as an energy storage device. The geometry of the device is also important because the larger the cross-sectional area is, the larger the capacitance is, and the smaller the gap is, the larger the capacitance is. So let's talk very briefly here about how a capacitor works, as it were. Okay. So imagine that I have this connected to some voltage source. Okay. This voltage source is going to be able to put some positive charge, let me draw it as a circle, on the top plate, which I'm going to call Q plus, and it's going to cause some negative charge Q minus to appear on the bottom plate. So we're always going to see that charge is balanced, okay? Now, the larger that voltage gets, the more charge we're going to put on the top and bottom plates. But it gets progressively harder and harder to place charge on these plates, right? Because we know, or at least those of us that have taken physics 202 know, that positive charges repel each other and negative charges repel each other. So as we try to cram more and more positive charge on the top plate, it gets harder and harder to do so because they don't want to be pushed close together. And the same thing for the negative plate, right? So what we are going to observe, particularly when we get into Friday's class, is that it's going to take time in order for us to charge and discharge a capacitor because of how it's harder and harder to add more charge to the system, okay? Now this adding charge to the system thing also actually describes how this device, which literally contains no conducting path, is able to have some amount of current flowing through it, right? Because we would expect that since there's no way to get charge to physically move from the top plate to the bottom plate, it should be impossible to have current. But because the amount of negative charge on the bottom plate has to match the amount of positive charge on the top plate, whenever we allow that charge to leave, we are going to see a current flow, right? So when positive charge leaves the top plate, we're going to have a current flowing up. And when negative charge leaves the bottom plate, we're also going to have a current flowing up. Similarly, when we're placing more charge on the plates, we're going to have a current flowing down through this device. This is what's called a displacement current, because we are displacing electrons up and down as we put more charge and take charge away from the plates, but it behaves the exact same way as every other current that we are dealing with. It's simply the movement of charge carriers, okay? So even though we're never actually causing charge to move from the top plate to the bottom plate, we can still observe a current flow by allowing charge to move on and off the plates. Okay. All right. So there is a relationship between the applied voltage and the amount of charge on the plates. And that relationship is as follows. Charge Q is equal to capacitance C multiplied by voltage V. So from this, we can see that capacitance can be defined as the ratio of the change in electric charge on an element due to a corresponding change in voltage. Or C is simply equal to charge over voltage. And from that, we can see that we have units of coulombs per volt, which is an amp second per volt, which we call a farad, symbol F. All right, so let's talk a bit about the circuit characteristics of a capacitor. And we're going to start by looking at capacitor symbols. So the first symbol that I'm going to give you guys is for a generic capacitor. And the symbol for a generic capacitor relies what it is made of, two parallel plates with leads sticking out for us to connect things to. Okay, so that's all the schematic symbol is for our general capacitor. If the voltage drop across the capacitor has this polarity, then we'll assume that our current has this polarity to obey the passive sign convention. Meaning that if current is flowing into the positive polarity terminal, we assume that the capacitor is absorbing power. The second symbol that you may see, not in this class, but if you're watching YouTube videos and all that kind of stuff to supplement things, or you're looking at particular circuit diagrams, you'll see this symbol where one of the plates appears to be curved. This is for an electrolytic or polarized capacitor. So in an electrolytic or polarized capacitor, the polarity of the voltage that you apply to the capacitor is incredibly important, because if you get it backwards, it bursts. If you have ever cracked open a computer or anything like that, and you've seen these cylindrical, like large cylindrical things with usually it looks like a metal plate on top, and there's usually either a line across the metal plate or an X across the metal plate. That's actually a groove cut in the metal so that when or if that capacitor bursts, that plate can deform without letting all of the stuff inside the capacitor, which could be dangerous chemicals, out. Okay? So typically speaking, if you see a cylindrical style capacitor, your best bet is to treat it as if it were an electrolytic capacitor. And there's usually a black strip on the casing that tells you which leg is the negative leg. It's also the shorter leg because they usually have a long leg and a short leg as well. Okay. For our generic capacitors, the legs are usually the same length, and it looks like, let me draw one. So it's usually a colored disc, something like this, with two legs sticking out of it, right? Whereas a cylindrical capacitor or an electrolytic capacitor would look something like this. Imagine that there's a black stripe here telling us where our negative polarity terminal is. One leg is longer than the other. In this class, in all of our labs and all that kind of stuff, we are only going to use generic capacitors because you guys, and myself included, don't pay enough attention about bothering how to hook things up most of the time, and I don't want to just blow them up constantly. Okay? But for very specific applications, you need to use polarized capacitor. Those are usually in the power supply portion of things where you need the voltages to be oriented in a particular way, and this forces that while also providing the energy that is necessary. Now, I want to say some textbooks use the electrolytic schematic symbol for all capacitors, which in my opinion is very wrong. And other people use them interchangeably, but technically speaking, that symbol has a very specific meaning only for electrolytic or polarized capacitors. So you won't see it in this class again, but you will absolutely see it watching YouTube videos, looking at schematic diagrams, this, that, and the other in your electrical engineering careers. Okay. So those are our symbols. Now let's talk about our current voltage relationships, right? So we know from literally the second day of class that current is simply the derivative of charge with respect to time. Well, in a capacitor, charge is related to voltage. So if we assume that the capacitance cannot change, what we will find is we will have C times the derivative of the capacitor voltage with respect to time is our first relationship. This is relationship number one. Just to refresh you guys on the inductor relationships, because I told you how similar these were. For an inductor, we had the relationship that VL was equal to L DI by dt. So these relationships are literally the same thing, except that everywhere we see current, we replace it with voltage and vice versa. Everywhere we see inductance, we replace it with capacitance. Every single relationship that we derive for capacitors will follow this one. Every last one of them, okay? So when we dealt with this derivative-based relationship for inductors, we were able to glean two things, right? For inductors, we saw that in a DC system, our inductor behaved like a short circuit, right? Because if the current does not change, then the derivative is zero, which means V is zero. So what do you think that relationship is going to be for capacitors? So if the voltage does not change, there's no current. Absolutely right. So what would we treat a capacitor like in a DC circuit? An open circuit. Absolutely right, which is exactly what I mentioned earlier. Okay. So our first relationship in a DC circuit capacitors behave like open circuits. Absolutely correct. Okay. What was the second relationship that we were able to glean from our derivative-based relationship for inductors? Anybody remember? Some of you guys hopefully took notes at some point last week. So to jog your memory, we looked at what happens when we had a time varying current waveform through the inductor and we change the rate at which the current rises. Right? And what we found is that the current flowing through an inductor cannot change abruptly because it would require an infinite transfer of energy in an infinitesimal amount of time. What do you think is going to happen for capacitors? So in an inductor, we said the current can't change abruptly. The voltage can't change abruptly for the exact same reason. So let me write this better. The voltage drop capacitor cannot change abruptly. And I believe I wrote this, so we'll say VC at T minus must equal VC at T plus. Just meaning our voltage needs to be a continuous function. It has to have a single value as we approach it from both sides. Approach any instant in time from both sides. So that's everything that we got from our derivative-based relationship. And again, it's very similar to what we had for the inductor relationships, except it's the exact opposite. We knew that we knew that V had to be 0 for inductors, which means I has to be 0 for capacitors. If the current can't change abruptly in an inductor, that means the voltage can't change abruptly in a capacitor. Again, I cannot stress this enough. Literally every single relationship that we're going to have is the exact same thing, except you swap current and voltage. Swap current and voltage and replace all your L's with C's and vice versa. Okay. So I think we're good on our derivative-based relationship here. So now we're going to do the exact same thing that we did to develop our next relationship. We're going to algebraically rearrange this and then take the derivative of both sides. And what that'll give us is that the voltage drop across a capacitor is equal to 1 over C times the integral from -infinity to T of IC T prime dt prime, or 1 over C, the integral from T naught to T of IC T prime dt prime plus VC at T naught. I'm not deriving it because it's literally the exact same derivation as we did for the inductor current. Now that we know the voltage drop and the current flowing through an inductor, we can say that through a capacitor, the power absorbed by a capacitor is simply I times V, which simplifies to C V dV by dt. And doing the exact same integration that we did last Wednesday, we can find that the energy stored by a capacitor is going to be given by 1/2 C times the capacitor voltage squared. So those are our 4 relationships. Not bothering to derive any of these last 3 because the derivation is literally exactly what I did last Wednesday. Applied in the exact same way as the example problem we worked last Wednesday, except that current and voltage is swapped, etc. So the last thing that I want to talk about is how we combine capacitors. How do you think that's going to work? The opposite way that it did for inductors. So let's not derive it. It's really pointless. We will see that capacitors in series combine like resistors in parallel, and capacitors in parallel combine like resistors in series. All right, done with the lecture in 31 minutes. And I started, I think, 7 minutes late. So, So, I mean, if you derive it, when you do Kirchhoff's voltage law and Kirchhoff's current law for these different things, you wind up getting the opposite relationships that you got for inductors, right? So when we derived the relationship for how inductors combined in series, we were adding up the voltage drops, and all those voltage drops were in terms of the derivative. Well, when we add up all those voltage drops in series here, all the voltages will be in terms of the integral. And vice versa. All right, so before we move along to the in-class assignment, I want to show you guys a couple of problems from the web work that I think are good problems. And what I mean by that is I like to put stuff like that on the test. Okay. So we're 14 homework assignments in or something like that into the web work, or maybe it's only 12, and I finally have a problem that I like. Yay. So we need it to be a continuous function, right? So it has to have the same value as you approach from the left as you approach from the right. So that means what it really means is there cannot be an instantaneous change. So as long as it takes time for it to change, everything is okay. But if at a single instant in time, the voltage has two different values for a capacitor, that means that we are transferring an infinite amount of charge, which cannot happen. Similarly, for an inductor, if the current has two different values at the same exact instant in time, that means that we are creating an infinitely large voltage, which means that we are transferring an infinite amount of energy in an infinitesimal amount of time, which physically cannot happen. So just to reiterate, as long as it takes time, and that time can be nanoseconds, we're still okay. If it takes nanoseconds for it to change, we're going to get a really large induced voltage or a really large induced current, but that's okay. But we cannot have literally an instantaneous change from, let's say, 5 volts to 2 volts for a capacitor without us creating charge. We'll talk quite a bit more about that concept of approaching time from the left and time from the right in Friday's class. Right. So, hold on, let me pull up something here. So let's see, I think we're at homework set number 12 here. So the problems that I'm going to bring to your attention are ones that typically contain both inductors and capacitors. And the reason why I like them is because it forces you to really learn about the relationships. So that's boring. So here's one. So in this problem, we have a simple, I think anyway, single loop circuit containing an inductor in series with a capacitor, right? And our goal here is to figure out what our source voltage is if we know what our capacitor voltage is. So let me write this information down, right? So this is homework 12, problem 3. Our circuit is this guy, Vs of t. Not that it matters, but yeah, it's inductor first. Capacitor over here. Does it define the polarity? Good. Just wanted to make sure. The quantity Vc of t is known. The quantity Vs of t is what we're trying to find. So anybody have any thoughts on how we might take a crack at a problem like this? Once again, I like to put stuff like this on your exam. So VC of t is a cosine function, so it is very much not a DC quantity. That would make things too easy. Right? So VC of t is some time varying function. So the expectation here, hopefully it makes sense, is that Vs of t will also be some time varying function. We have to figure out what it is. Right? So I feel like I gave you guys a huge hint when I described this problem as a single loop circuit, because everything is connected in series. Whenever we have a single loop circuit, what should we do? Kirchhoff's voltage law. 100% of the time, that's how we should look at a single loop circuit, okay? So what I'm going to do is I'm just going to call the voltage drop across my inductor VL of t, and I'm going to call the current flowing through my circuit I of t, where this current I of t represents both the inductor current and the capacitor current. Right? So if I apply Kirchhoff's voltage law, I can see that Vs of t is VL of t plus Vc of t. Vc of t was given to us, so that's how do we get VL of t? L di by dt, okay? How do we get I of t? So we will use VC, so what's the relationship? dV dt, yeah. So there we go. Without knowing it, you guys are effectively solving a second order differential equation. So if you can do the derivative of a cosine function, or really the second derivative of a cosine function, you're good to go here, right? Nothing hard. It's simply just using the relationships, making them work together based on the quantities that you know. So this is homework 12, problem 3. In a nutshell, I've told you how to get the answer. You have to go through the calculus of actually determining what it is, paying attention to units and all that kind of jazz. Any questions about anything here? Fairly straightforward, right? We had a single loop circuit, we applied KVL, and we used our capacitor and inductor current voltage relationships to develop an equation that depends only on a quantity that we were given. Right, so you're given L, you're given C, and you're given VC of t, and it's literally asking for a function of time. So you simply do that second derivative, plug the numbers in, and Bob's your uncle. That's just a boring graph thing. Homework 12, problem 5. I really like this one too. So when I redraw it here in a moment, we can see that we have two capacitors in series. I'm just going to replace them with a single equivalent capacitance so that our life is ever so slightly easier. So effectively, our circuit is, I think this is a voltage source, yeah. Here's Vs of t. Here's C. Here's L. We are told that this is our direction for Is of t. So I believe we are given Vs of t is a known quantity. And once again, it's a time varying quantity. And we are given Is of 0. What we want to find, if I am not mistaken, is Is of t. Yep, so we're given Vs, we're given Is at 0, we're asked to find Is for t greater than 0. We have the value of our capacitor and we have the value of our inductor. So this is a single node pair circuit, which means everything is connected in parallel. So what should our first step be? There we go. Anytime we have a single node pair circuit, Kirchhoff's current law is where we should be starting. So I am going to label this as my capacitor current, direction down. This is my inductor current, direction down, so that I can say Is of t is equal to IC plus IL. Anybody have any problem with that? Just good old Kirchhoff's current law from the second day of class, but now we have time varying things. So because all of these elements are connected in parallel, that means they all have the same voltage drop, right? So much like we saw in that single loop circuit where we were expressing things in terms of I, now we're going to be expressing things in terms of V. So what's the relationship between the voltage drop across the capacitor and the current flowing through a capacitor? Yep. C dV by dt. And in this case, that VC is just going to be Vs. Right? What's the relationship for an inductor? But we don't know how. We know V. So it's not going to be the derivative-based relationship, it's going to be the integral-based relationship. Right? So that means we're going to have 1 over L times the integral from T naught to T of Vs of T prime dt prime plus IL at T naught. So This part is all fairly straightforward because it's just doing calculus on known quantities. Right? We're taking the derivative of that voltage relationship that we were given for the first part. We're taking the integral of that voltage relationship for the second part. But this IL at T naught bit is a piece of information that I don't think we currently have. Okay. All right. We were given IS at 0. But we need IL at 0 to solve for IS for all points in time. So how are we going to figure out what IL at 0 is? What did you say, Emily? So Mason is on the right track here. Okay. So he suggested that IL is equal to IS minus IC. Now this is true because Kirchhoff's current law tells us it is. But what we're going to do is specifically find those things at 0, because KCL has to be true for literally all points in time, which means it's true for an individual point in time as well. Right? So KCL at T is equal to 0 will allow us to solve for IL at T is equal to 0. IS was given to us. How do we find IC at 0? Take the derivative and set T is equal to 0. Absolutely right. Right. Now we have all of the parts, and it's simply plugging things in and then combining like terms and all that kind of good stuff. So once again, I really like these two problems because it makes you think about all of the different, or at least the different current and voltage relationships for capacitors and inductors and the relationships between them. Okay. So if you look at the old tests, you will definitely see problems like this on them. You should expect problems like this on the new test as well. Okay. So these are legitimately 2 of the 100-ish problems that are assigned to you guys in this class, and they're practically the only ones that I like. So just trying to give you fair warning, expect something like this on your exam.